Dear teachers and classmates, good morning everyone. Today our group will give a report on the implementation and core results of our action research, focusing on the theme of improving high school students' mathematics problem-solving abilities through cooperative learning. There are 8 members in our research group, and the student IDs of all members have been listed on the screen. Next, we will work together to complete this report.
Next is the abstract. We wanted to check if a structured group cooperation learning model works for senior high students' math problem solving. We focus on fixing 3 big issues: methodological reasoning, disorganized solution steps, and unfair participation in real-world application tasks. We did a 2-week classroom action research. The topic was the binomial theory for grade 11 students. We used the framework, first divided tasks, then gave peer feedback, and finally do group presentations. To collect data, we used the pre-test, post-test, classroom organization, and student questionnaires. The results are clear. The pre-test average score was 72.17 with a standard deviation of 16.187. The post-test average went up to 18.14, and the standard deviation dropped to 11.571. Logical competence of solutions rose by 26.3%, and low achiever active participation went up by 13.5%. Also, the score gap between top and low students got smaller by 8.2 points. This proves cooperative learning can make problem solving better and work as a good teaching method for high school math. Now let's talk about why we did this study. This is the research background. First, China's recent math curriculum reform say problem solving ability is a core skill for students. But in real teaching, students struggle with known routine, real-life math problems. For example, our target students' data shows grade 11 students only get 58.3% on average for application question, while lower than their scores on basic procedure question. Another reason is the old teaching method. Most classes still use direct instruction. Teacher talk students listen, then do practice alone. This stops students from engaging more, interacting with peers, and developing their thinking skill. But cooperative learning, which comes from Vygotsky's social constructivist theory, can fix this. It encourages structured group work, but is not used much in Chinese high school math classes. That's why we did this study.
Part 4. Problem statement and the research objective. Let's move it to the problem we found at our research goals. First, the problems. Students are much worse at applications questions than the BCQ questions. This is a big gap between when the curriculum wants at what students can do. The old lecture style class are teacher-centered. Students can't engage deeply at even after class, then can't solve a similar problem alone. Also, only top students ask real questions in class. Low achievers hardly get to participate. What's more, teachers only see students finally as well, not how the thought zero the problem. Feedback is solved too, so it don't help much. To fix this, we set 4 goals. First, develop a cooperative learning model that works from math application questions. Second, help students get better at logical reasoning and working in groups. Third, check how cooperative learning affects problem solving both with numbers and really observations. Fourth, give math teachers a practical is-to-cop teaching framework. Part 5. Research question, significance and scope. Now, 3 key research questions guided our study. First, how does cooperative learning change how students organize their logic when solving math problems? Second, which part of cooperative learning devising, pre-feedback, or group presentation helps improve problem solving most. Third, can cooperative learning make the skill gap between students with different math skills smaller? This study matters in three ways. Theoretically, it makes Vygotsky's social constructivity theory more useful in math problem solving teaching. Practically, it gives high school math teachers a clear, flexible, cooperative learning frameworks. Innovatively, we slip problem solving into small, quantitative tasks that students can share and made release from pre-assessment. This gets students more engaged. About the scope, we did a study in grade 11 math class of the private high school in China. The whole study lasted 1 semester, but the cooperative learning part was 2 weeks. There are limitations too. We only used studies from one school, so results might not apply everywhere. Also, how teachers run a program and how group work could affect outcomes.
We also looked back at past teaching in our target class. The class is grade 11 at Shenzhen Elite Experiment Secondary School, also called Jinhua Middle School. There are 36 students with different math levels and learning styles. In daily math classes, there were big problems. Students could do standard textbook exercises by following steps, but they struggle with no routine tasks that needed flexible thinking. Many just memorized formulas instead of understanding the reasoning. Also, only a few students participate in discussion or group work. Low achievers were usually quiet. Even when we tried group work before, it was superficial. Students were in groups, but they didn't really work together. Some students just let others do the work. We also found that students' thinking was hidden. Teachers only saw final answers, not how they get there. Feedback was slow too. Homework was marked and returned days later, so students could fix mistakes in time. That's why we chose the binomial theorem as our focus topic. It needs understanding of algebra, combinatorics, and patterns, which are key for problem solving. We also read other studies. This is a literature review. Fadiline in 2019 found that the group investigation cooperative model made students better at problem solving and more motivated. Tracking in 2022 and Najun in 2024 studied the team assessment individualization model. They found TAI improved problem-solving, communication skills, and self-confidence in math. But there are gaps in these studies. Most were done in colleges or vocational schools. Not many in senior high math classes. They also focused on short-term effects, not long-term ones. Few studies were led by teachers in real classrooms, and not many looked at how group dynamic affect problem solving in mixed ability groups. Our study fills these gaps. We did action research in a real high school math classes, and we improved the model by reflecting on each STEM. This gives practical ideas for using group work in high school math long term.
Now, how did we do the research? Let's talk about the methodology. We use classroom action research with the plan, action, observe, reflection cycle. It was a single group pre-test and post-test design 36 grade 11 students, 2-week intervention, focus on binomial theorem application questions. The 36 students were 18 boys and 18 girls with mixed abilities, 25% high achievers, 50% medium, and 25% low. We collect data in 3 ways. First, pre-test and post-test. 100-point papers with basic application, 30 points. Logical reasoning, 40 points, and contextual modeling, 30 points. The test was reliable. Content validity 0.89. Cron box alpha 0.85. Second, classroom observations. We watch three things: if real works well, how students interact, and if tasks were finished. The agreement rate ICC was 0.86. Third, questionnaire. A 5-point Likert scale with 50 questions, covering 4 dimensions of cooperative learning. His Cron box alpha is 0.83, so the data is reliable. For data analysis, we used quantitative methods, paired t-tests to compare pre- and post scores, ANOVA to check gaps between groups, Pearson correlation to see relationships. We also did qualitative analysis, called observation data, to find how cooperative learning helps logical reasoning. We follow ethics to got consent from schools, teachers, students, and parents, anonymize data, and let students quiz without impact on grades. After setting the research method, we start the specific implementation. This page is about the core design framework. First, group structure. 6-member heterogeneous groups with 2 roles, leader and members. Leaders assign tasks and control progress. Members finish their tasks and report in turns. This simplifies operations but keeps cooperative learning's core value. Second, test process. We follow the concrete to abstract quantity rule. Week 1, use item distribution and other specific problems to help students master basic binomial serial applications. Week 2, use complex problems like probability calculations to improve knowledge transfer. Third, theoretical foundation. 3 theories support the framework. Vygotsky-per scaffolding. Interaction promotes cognitive development. Johnson and Johnson's positive interdependence. Role complementarity aligns group and individual goals. And APOS theory. Students internalize concepts through 4 progressive stages. Fourth, instructional model. We use the progressive release of responsibility model. At first, teachers demonstrate cooperation. Then, teachers give hints only when groups are stuck. Finally, students collaborate independently. This fits curriculum standards and is easy to promote. Let's look at the daily plan. Week 1 was for building foundations. On one day, we gave a 40-minute protest with 10 questions to check students' initial skills. On days 2 to 3, we spent 5 minutes training group leaders, then 30 minutes for groups to solve basic problems, and 5 minutes sharing typical cases. On days 4 to 5, we did a 5-minute warm-up review, 30 minutes of group structure tests, and 5 minutes for teachers to check if task division was reasonable. Week 2 was for application expansion. On days 6 to 7, we used 5 minutes to show how to solve complex problems, 25 minutes for group cooperation, and 10 minutes for intergroup review. On days 8 to 9, groups spent 30 minutes presenting their problem-solving ideas, 7 minutes for peers to ask questions and add details, and 3 minutes for teacher summary. On day 10, we gave a 35-minute protest and a 5-minute short questionnaire to collect students' feedback on cooperative learning. During the observation phase, we used a lightweight tracking method because teachers are busy. We prepared a shorthand table with group numbers. When working around the classroom, we focused on 3 things. First, the group leaders finished task division within 2 minutes. We marked it with correct or incorrect. Second, the low achievers speak at least once per class. We wrote down the number of times directly. Third, what percentage of the group test was finished? We estimate the percentage. In the reflection phase, we found 2 key points. The 2-role framework, leader and member, made classroom organization much easier, and 6-person groups balanced test, diversity, and participation. Too many people would cause uneven participation, but we also found room for improvement. Some group leaders can't control time well, so tests took too long. Later, we needed to add a test division template. Also, low achievers sometimes become bystanders in complex tests, so group leaders should align space subtests to learn in advance to boost their participation.
This page focuses on the analysis of pre-test and post-test data. First, the overall score change SPSS analysis shows the pretest average score was 72.17 SD equals 16.187, while the post-test average rose to 80.14 SD, 11.571, a difference of 7.97 points. The paired samples t-tests gave a t-value of 6.450 and p 0.01, which means the score improvement after the intervention is statistically significant. Looking at score band changes, in the pre-test, 9 students, 25%, were in the low score band 60 points. In the post-test, only 2 students, 5.6%, remained in this band. For the high score band is greater than or equal to 80 points, the number of students increased from 1438.9% in the pre-test to 2055.6% in the post-test. The number of medium score students, 60 to 79 points, was relatively stable, rising slightly from 13 to 14. This change clearly shows cooperative learning reduced the number of low score students and increased high score students. There were also differences in improvement across ability groups. One way ANOVA revealed that low achievers who were in the low score band in the pretest had the most obvious improvement, with their average score rising by 9.17 points from 49.33 to 58.50. Medium achievers improved by 6.5 points from 71.85 to 78.35, while high achievers had a smaller improvement of 3.8 points from 87.14 to 90.94. Finally, the score gap between high achievers and low achievers narrowed by 8.2 points, which fully proves cooperative learning can effectively reduce the achievement gap between students of different abilities. Next, questionnaires results. The questionnaire had 15 questions, and we collected 36 valid responses. The Chromebox alpha coefficient was 0.879, which is much higher than the 0.7 threshold for reliable data. Students' overall rating of cooperative learning was 3.64 out of 5, close to agree. Among the 4 dimensions, cooperative task clarity got the highest score, 3.74, followed by participation motivation, 3.72, peer feedback validity 3.59, and logic enhancement perception 3.57 were slightly lower, but all were above the 3-point midpoint. This shows students generally recognize the positive effects of cooperative learning. We also found key mechanisms linking cooperative learning to results. First, clear task division was central. Classroom observations showed groups with clear division had higher task completion rates or equals 0.82 and more active low achievers or equals 0.79. Questionnaires data also proved task clarity was strongly related to overall learning experience or equals 0.799 and perceived logic improvement or equals 0.534. Second, peer feedback played a mediating role. It was moderately related to score improvement, R equals 0.62, and highly related to perceived logic improvement, R equals 0.712. Immediate feedback helped fix reasoning gaps. Third, participation linked to achievement. Low achievers' participation went from 1.9 to 4.25 times per class, and their score improvement, 9.17 points, was much bigger than high achievers' 3.8 points. This fits Vygotsky's zone of proximal development theory. Proper guidance helps students make big progress.
Finally, let's summarize the conclusion and give recommendations. The study shows the structured cooperative learning model with 6-person makes the ability groups, 2 roles, leader and member, and lightweight observation tools effectively improve high school students' problem-solving skills in the binomial theorem. Especially post-test scores increased by 5.12 points. Logical completeness of solutions rose by 26.3%. Low achievers' participation rate went by up 1 to 1.2%, and the score gap between high and low achievers narrowed by
8.2 points. These results fix key math teaching problems like fragmented logical and unfair participation and meet the 2022 Ministry of Education curriculum standard that emphasize active exploration and collaborative problem solving. For teachers, there are 4 suggestions. First, add cooperative tasks to lesson plans and design real-world tasks that need role collaboration. Second, use two-role framework and let group leaders rotate. This gives more students a chance to take responsibility. Third, use a 1-minute task division template to reduce the burden on group leaders. Fourth, train students per feedback skills to make feedback more targeted and effective. Also assign different roles to low achievers. Start with basic tasks, then slowly increase difficulty to help them build confidence. For future research, we have 3 ideas. First, extend the intervention to 6 weeks and add a delayed post-test to check long-term effects on knowledge retention. Second, do cross-school studies in different regions and school types like key schools and ordinary schools to make the model more adaptable. Third, compare the two-role framework with multi-role models to find the best group structure for abstract math learning. These studies will make the cooperative learning model better, provide stronger support for improving students' high-level math thinking, and help innovate math teaching methods.
That's all for our research report. Thank you for listening. If you have any questions or suggestions, please feel free to share them with us.